There are these invisible forces all around us, happening all the time. Think about the fizz when you open a soda or the battery keeping your phone alive. Those are all chemical reactions. And a lot of them have this really obvious side effect. Things get hot or they get cold. Today, we're going to pull back the curtain on the science behind that feeling. We're going to get to the bottom of why that happens. I mean, it seems like a pretty simple question, right? On the one hand, you've got a campfire, just wood burning, and it's throwing off this incredible cozy heat. But on the other hand, you have one of those instant cold packs. You just squeeze it and suddenly it gets intensely, shockingly cold. They're both just chemical reactions, but they could not be more opposite. So what's the deal? Well, that's the big mystery we are solving in this explainer. And here's our game plan for figuring it all out. We're going to start with the basics of how energy moves around. Then we'll get into a super important concept called enthalpy. We'll look at the two personalities that every reaction has, why scientists needed to create some rules for this stuff, and finally, how they actually measure it all. All right, first things first, let's lock in the one fundamental idea that makes all of this work. This right here, this is the core concept. Just think of the system as the chemicals themselves, the actual stuff that's reacting. And the surroundings? Well, that's literally everything else. The beaker, the air, your hand if you're holding it. So what we feel as hot or cold is just the direction that energy is flowing. Is the reaction giving energy out to its surroundings, or is it pulling energy in? Now, to really talk about this like a chemist, we need a name for all that energy that's stored up inside the chemicals to begin with. And that name is enthalpy. It's basically all the potential chemical energy that's locked away inside a substance. But, and this is a big but, there's a huge catch. It's pretty much impossible to measure the total enthalpy of anything. And there's a fantastic way to wrap your head around why that is. This analogy just nails it, doesn't it? Trying to measure total enthalpy would be like trying to get the exact volume of the entire Pacific Ocean. I mean, you'd have to account for every single trench, every underwater volcano. It's just way too complex. But what you can do, very easily, is measure if the sea level goes up or down. And that's exactly what chemists do with energy. So while we can't measure the total, we can be incredibly precise about measuring the change in enthalpy that happens during a reaction. We call this the enthalpy change, or for short, delta H. That little triangle is the Greek letter delta, and in science, it just means change in. This number, delta H, is our change in sea level. It's the key that tells us if energy flowed out or in. Okay, so now we have our key, delta H. Let's use it to finally unlock the mystery of that campfire and the cold pack. Because really, all reactions have one of two personalities, and it all depends on which way that energy is flowing. And this lays it all out perfectly. On the left, you've got your exothermic reactions. That's our campfire. Heat flows out of the system, so the surroundings, that's us, get hotter. And for these, delta H is always a negative number. On the right, you have endothermic reactions. That's the cold pack. It has to pull heat into the system from its surroundings, which is why your hand feels so cold when you touch it. Its delta H is always positive. Let's picture that for a second. An exothermic reaction starts with chemicals that are packed with a lot of energy. They're like a ball sitting at the very top of a hill. Then, the reaction kicks off, and whoosh, all that energy gets released. The things you're left with, the products, are now in a much lower, much more stable energy state, just like that ball now resting peacefully at the bottom of the hill. So you can probably guess what an endothermic reaction looks like, right? It's the exact opposite. The starting chemicals are at a low energy state, and to make the reaction happen, the system has to suck in energy from the outside world. It uses that energy to build the products, which now have a higher energy level than what you started with. It's literally like having to push that ball all the way back up the hill. It takes energy. So we get what delta H is, and we know if it's positive or negative. But how do scientists measure it so that everyone's results are comparable? Well, they had to create a level playing field. And this is a really important question. The amount of energy a reaction releases can actually change depending on, say, the temperature in the lab or even the air pressure. So if a scientist in high-altitude Denver gets one result and another in sea-level Miami gets a different one, how do they know if the chemistry is different or if it was just the environment? They needed a set of agreed-upon rules. And these are the rules of the game. They're called standard conditions. The pressure has to be 100 kilopascals, which is just about normal atmospheric pressure. The temperature has to be 298 Kelvin, which is a nice, comfortable 25 degrees Celsius or 77 Fahrenheit. And whatever you're testing has to be in its normal state. You know, water is a liquid, oxygen is a gas, and so on. So now when you're looking at chemical data and you see a delta H with this little circle symbol next to it, that's your clue. It tells you, hey, this measurement was taken following all those rules. It means scientists anywhere in the world can trust that result and compare it to their own. All right, we have the concept and we have the rules. Now for the last piece of the puzzle, the actual tool. How in the world do you measure heat energy? Well, the science is called calorimetry. And it's the hands-on, practical way we can find the value of delta H. It's how we can actually prove everything we've been talking about with a real measurement. And you might be surprised by this, but a calorimeter can be incredibly simple. A lot of the time, it's basically a fancy coffee cup. Just a polystyrene cup to trap the heat, a lid to stop it from escaping, and a thermometer poked through the top. The whole idea is to trap the reaction and force all of its energy, whether it's giving it off or sucking it in, to affect a specific amount of water that you've put inside. This is the key equation that makes it all work. Q equals mc delta T. Now, Q is the heat energy we're trying to find, and to get it, we just need to know m, the mass of the water, C, which is just a known constant for water, and delta T, which is simply the change in temperature that we measured on our thermometer. So the process is actually pretty straightforward. First, you use that equation to figure out Q, the total heat the water gained or lost. Next, you figure out exactly how much of your chemical actually reacted, using a unit called moles. And finally, you just divide the total heat by the amount of chemical that reacted. And bam, that gives you the energy change per mole, which is our old friend, delta H. And that's really the big takeaway here. It all boils down to something so simple. We let a reaction happen, we let it warm up or cool down some water, we measure that tiny change in temperature, and with a bit of simple math, we can figure out the powerful, fundamental energy that was locked away in those chemical bonds. Which leaves us with one last big question to chew on. We've been talking about energy moving from the system to the surroundings, but a basic law of physics says energy can't be created or destroyed, right? So when your campfire finally burns out and goes cold, where did all of that incredible heat energy actually go? It didn't just disappear. It's a great question, and the answer opens up a whole new world of science. Thanks so much for joining me on this explainer.